Okay, I want to give this last video on introduction to matrices, where we're just going to wrap up some loose ends and give you some insight, some other little things about matrices that you kind of should just keep in mind. Before I do that, I want to talk about one more application that is near and dear to me. I'm a chemist, so I kind of can see things a little in a weird way, or have seen things in a weird way. And one thing that I use a ton of matrices in is something called group theory. Now, you probably have this book on your bookshelf, a little dusty, but it's Chemical Applications of Group Theory by F.A. Cotton. It's a great book, great, nice bedtime reading. But what it talks about is it looks at how molecules do things. So, for example, if I take something like that, you've probably seen it, it's water. The water molecule has lots of things of symmetry. By symmetry, I literally mean symmetrical. For example, I could break it down the center and it's symmetrical that way. I could also break it on the plane of the board, symmetrical that way. I think that's about it. Because if I go down this axis, it's not symmetrical, or that axis, it's not. That's pretty much it, right? Some other things about water is I can go down the center like this and rotate. That will be symmetry, 180 degrees rotational symmetry. If I go along the hydrogen axis or the other hydrogen axis, no, that is not symmetrical. Now, why we care about this is when you look at how energy is partitioned into the molecule. What I'm saying is, if I heat this thing up, that energy has to go somewhere, and in a molecule, the energy goes into vibrations or twists or shakes. And how a molecule vibrates, and by vibrates, I literally mean something like this. Where this guy might go like that, where this one goes out, this one goes in, and then on the flip side, one goes out and one goes in. So it's going back and forth, back and forth. When it does that, heads up, the center mass has to stay in the same place, but we'll ignore that. Anyways, how this happens, and these little twists and shakes and vibrations, all of that is modeled and studied with group theory. And this right here, whole book on group theory, and how the matrix world comes into it is we have these called character tables. Character tables for chemically important symmetry groups. And so you can dig through here, figure out the group that is, which we're going to kind of skip that part. But it has a table, see if you can see this. It has a table you can see for a C6 molecule, see the 1, 1, 1 and negative ones. This is the matrix that tells you what the molecule does in 3D space. There's whole piles and piles of these. You can keep going through this. So again, go grab it off your bookshelf, take a look at it. It's fun stuff. Okay, so let's talk about some other matrix sort of stuff. Okay. Bye-bye water. Again, this is just kind of some loose ends. Remember that plus and minus, the dimensions of the sum or the difference will be the same. Okay, but multiplication and division are not the same. So we got to look at this here. So if I have a matrix where the dimensions are m times n, Okay, so rows, columns, and I take that matrix and I multiply it by one that is n rows by k columns. So m rows by n columns multiplied by n rows by k columns. The product, the resultant of those, you'll notice that these two are the same. Because those two are the same, this is going to be a defined answer. Okay, so I'm gonna put a smiley face here. This is defined. And this will be clear in a few minutes. We're gonna go through an example. Now, the dimensions of the product here is going to be m by k. So m right there and k right there. Okay, and we saw this in the previous one where Jim bought the cars. Jim was trying to make an order for cars. Jim had a 2, so his was, I forget the numbers here, but he had say an M and an N, and the other one over here, remember his was 1 by 2, and the other one over here was 1, 2, 3 by 2. Oh, rows by columns, 2 by 3. Okay, and you can see, let's just put this in here. Okay, you can see that those two are the same, so we can get an answer. And then my product over here was 1 by 3, so it was long and skinny, like that. And we saw that earlier, so not news. I just want to give you a heads up. If these two inner numbers are not the same, your product will be undefined. You know, like a multiplication by 0 or something like that in there. Okay. Okay, another thing with matrix multiplication is the commutative property. You're probably asking about this, so let's just nail it now. For something to be commutative, that is this. That's A times B equals B times A. So in the normal math world, something like 3 times 6 equals 6 times 3. 18 is 18. Good to go. With traditional multiplication, it doesn't matter which way we do this. With matrix multiplication, things are different. Okay, so let's try this out. So I'm going to do 2 matrices. A is 1, 1, 2, 1. And B is 2, 1, 1, 1. Okay? I'm going to go ahead and multiply these both ways. I'm going to do A times B, then we're also going to do B times A. So, A times B, 1, 1, 2, 1. 2, 1, 1, 1. Okay, little recap on multiplication. Well, first place, what's my dimension going to be over there? Okay, so this is 2 by 2 times 2 by 2. So yes, those guys are the same, so we can do that. And my dimensions are the outers, so it's going to be 2 by 2. So I'm going to have another square matrix out there. Okay, so 1 times 2 plus 1 times 1. Okay? 1 times 1 plus 1 times 1. Okay? Next, 2 times 2. I'm just going to jump to it. 2 times 2 plus 1 times 1. And the last one, 2 times 1 plus 1 times 1. And let's see what's that going to be. 2 and 1, so 3, 2, 5, 3. Okay? That's A times B. Let's do the other way around. B times A. So 2, 1, 1, 1 times 1, 1, 2, 1. Let me get some emphasize what we're doing here. So 2 times 1 plus 2 times 1, 4. 2 times 1 plus 1 times 1, 3. 1 times 1 plus 2 times 1, 3, 1, 1, 2. Okay. Those two products are not the same. That's A times B. This is B times A. Clearly not the same. So, matrix multiplication matters, the direction you go. Okay, so 2 ways you can show that. One is look at the dimensions. If the dimensions don't work out, then you stop, because if those inner numbers aren't the same, right here, you can't multiply them. Second is just by demonstrating it, as we just did here. There's 2 ways to show it. Okay, a couple more loose ends. A matrix that's just up and down, 3, 5, 6, that's a matrix. What are its dimensions? Okay, this is 3 by 1, 3 rows, 1 column. This is called a column vector. Yeah, we just kind of crossed into vectors for a quick sec. But 3 by 1 is a column vector. You can kind of guess what it is going the other way. 6, 9, 0. Okay, this here is a 1 by 3. 1 row, 3 columns. And this is called a row vector. Hey, can I multiply these together? Yes, I can. I can multiply them together because these inner numbers are the same. And my product is going to be a 3 by 3 vector. Okay? Just while we're there. Okay, a couple of little random ones. A vector that looks like this. All zeros. All zeros, this is called the 0 vector. This is the 0 vector. I'm sorry, the 0 matrix. I got the vector word stuck in my head. This is the 0 matrix. This is equivalent to the number 0 in our typical math system, okay? You multiply a matrix by that, you get 0. It's also called the additive identity matrix. I'm not sure why. Okay, the other one is called the identity matrix. And the identity matrix is equivalent to the number 1 in our system. I wrote a very simplified one. So if you multiply any 3 by 3 by this one, you will get the same product over here. Okay, this is just number 1. If your dimensions are not nice, clean, and square, you will not necessarily have the ones on a diagonal. They may be somewhere else. There are an infinite number of identity matrices. However, the takeaway is that your matrix times the identity matrix returns your same matrix. So this one here is not always going to be ones on a diagonal, because if you have a matrix that's like a 3 by 2, you aren't going to have ones on a diagonal. It'll be a 1 up in a corner somewhere. So you might have to do a little legwork to figure that out. And I believe this is it for some of the matrix loose ends. So I've wrapped up intro to matrices, addition, subtraction, multiplication, commutative property, talk about rows and vectors, 0, identity, handful of examples and applications, and multiplication. Multiplication is a big one. Next up, we will look at determinants and some other ways to use matrices to solve problems, including systems of equations and just some other applications.